Our next way of seeing a relation is via a mapping diagram. This is a mapping diagram. It's kind of like a table, but instead of all of the points being listed out horizontally of like, here's your x and here's your y, it's like your -3 goes to -1. And that's all a mapping diagram is. So your point would be -3, -1, or -1, -2. In order to determine whether a mapping diagram is a function, we review the arrows. The relation will not be a function if any x value or any input here maps to more than one different output. Okay, so if any one of these inputs right here, any one of these x values goes to two different or three different y values, then it is not a function. This guy, while -3 and 1 both go to -1, that's totally fine because -3 is only going there. Okay, whereas 1 over here is going to both -1 and 0. You can think of this if you're trying to think of like an analogy or a story to tell yourself while you're trying to figure out whether something is a function or not. Imagine if you showed up to school and you asked a person, what classroom is my math class in? And somebody said, oh, well, it's in room 409 and 302. And you would be like, that doesn't give me an answer at all. That's two different places. How can I go to two different places? That's kind of the same idea of a function, of like, if we show up and we put ourselves into this machine of where is my math class, you should be getting one answer back. If you get two, it's confusing. So imagine yourself as the input and imagine that you want an output that's just one output. Now, you could go to room 302 and all of your friends could go to room 302, but that's fine. You've answered where is the math class. You just all happen to be in the same math class, and that's fine. Whereas if you were told to go to two different math classes, it would not be fine. Hopefully that helps. Okay, the last thing, so this is a function, this is not. The last way that we're going to do it, to try this, is to look at it algebraically. So what we need to do is we need to get y by itself. And the equation will not be a function if you have this idea of a plus or minus sign. So here if I got y by itself, I would get y equals -x² plus 1. And that's fine. We know that that's a parabola, and we know from looking at our graph that a parabola, no matter what, will pass the vertical line test. So that's fine. It is a function. Versus if we tried to get y alone here, we would get y² equals x plus 1. And it's still not by itself because it had this squared piece. So I need to take the square root of both sides. Y equals, and this is where your plus or minus comes in. Mostly what we're looking at for whether or not it's a function is really we're looking at is y squared. It's fine if x is squared. Totally fine. Parabola, absolutely fine. But if y is squared, this is when y is squared. It is not a function. Also, when y is squared and x is squared, that's the equation of a circle. And if you think about the graph of a circle, so this is supposed to represent functions, but the graph of a circle would not pass the vertical line test. So pretty much what you're looking for is if y is squared in an algebraic expression or an algebraic equation, then it is not a function. So that is function versus not function, and we've talked about evaluating functions. So we're learning a lot here. We're making moves. Hopefully everything's feeling okay. If not, set up a time, talk to me or Mr. Serene. Either are okay. Even if you're in the other class, we're both here for you at any point. The last thing, not the last thing, but a few more things that we wanted to talk about in class today is finding domain and range, and then a few more pieces on evaluating equations, evaluating functions. Okay, so as we talked about earlier, the domain is the set of all possible x values, whereas the range is the set of all possible y values. We're going to identify the domain and range of the relationships in the table, set notation, and graph examples from before. So they're right here. Let me zoom out a little bit. So from our table A, our domain here is just a set of numbers because your table is the beginning and end of this relation. It doesn't say, hey, this is just some points from a line. This is just, hey, this is the relation. So your domain here is the set of all x values. Remember that set is in curly brackets. And then we say it's your x values such that. So you say curly bracket, hey, it's the set. And then, hey, we're representing x values such that x is equal to -1, 0, and 1. And then you close your curly bracket. We're defining our variable, and then we're saying, hey, as long as x is equal to these values. You can do the same thing for your range. Your range is 1, 0, and 1, which means that your range is your y values such that y equals 0 and 1. You do not need to list 1 twice. It just stays once because that's all it is. It's just 1. Okay, let's try it again. B, your domain, is the set of all x values such that x is equal to 2 and 3. Only 2 and 3. Whereas R is the set of y values such that y equals 8, 10, and 11. You don't have to order it from least to greatest. I just do because I think it looks nicer when it's ordered from smallest to largest. Okay, so your domain is all of the x values that go into this relationship. And so sometimes it's only 3 x values that go into a relationship, and then you're done. Same with these points right here, right? If we're talking about C, your domain is x such that x equals 2, 3, and 4. Your range is y such that y equals -1 and then 3. D, your domain is 0 and 1. Your range is -3, -2, and 8. Hopefully it's making a little bit of sense. It's staying consistent so far that we've got only a certain amount of points that are in this relation in our first 4 examples. Whereas on E and F, we have graphed equations. And graphed equations are the set of all possible points. There's infinite points on a line. So if we want to talk about all of our possible x values for domain, we can't just list values. We can't just be like, 3, 2, 4, 1, 5, because these arrows insinuate or imply that we're going to keep going forever and ever and ever and ever and ever, which means that all of these x values will also be counted. But then also you can have a point 3.5. You can have a point at 1.5. You know, so you can be in between as well. So you can't just list values. You need to give a range of values that would work. With parabolas, your x values with quadratics, your x values, you have no restrictions. You can put in any x value that you want anytime. It goes forever and ever and ever. It'll get like really, really steep, but it will still technically keep going on either side of those either side of the x-axis for forever. How we represent that is x such that x exists in, so it's this almost euro symbol, but slightly less than the euro symbol, and then it exists in the real numbers. This fancy R that's got a little like bold piece is our mathematical notation for real numbers. You could also say between -infinity and positive infinity. So instead of x exists in the real numbers, you could have done between -infinity and positive infinity. That would have been fine as well. I'll show you how to write that in our next example. Our range with parabolas is not quite all real numbers because the way that the parabola behaves. The way that a parabola behaves is that it has a minimum. There's a place where it goes to that you can't get any farther below on that graph. There is no y value below that vertex. That vertex in this case is 3, -1. So at 3, -1, we'll never be below that y value, which means that we have to be greater than or equal to -1. So you could say y such that y is greater than or equal to -1. So with quadratics, we do have restrictions, but with quadratics specifically only on our range. Okay, for f, this is the inverse of a quadratic, so it's slightly different. Things will be a little flipped around. Notice that with your range, you now have any possible y values, that this parabola will keep going up and up in a really slow way, but you could always have a positive y value and always have a negative y value. So your range is y such that, and you could say y exists in the real numbers. Or you could say, okay, well then y lives between -infinity and positive infinity. That's a different way you could write it. Notice I never say or equals to with infinity because you can't equal infinity. It's an idea, not a number. Okay, versus our domain. Our domain is restricted with this graph because we are at here at 0, 0, and we could be less than that on our x-axis, but we'll never be positive from there, which means that we are x such that, and we could say x is less than or equal to 0, or you could say from -infinity less than x, which is less than or equal to 0. Strictly less than because you can never be equal to infinity, less than or equal to 0 because you do touch 0. Your vertex in this case is 0. So there's a lot of things to think about when you're talking about domain. Creating this idea of the set of all of the x values and the set of all of the y values looks different when we're talking about like tables and points versus when we're talking about an actual line or a curve that continues on for forever and ever. You need to, if you have a curve or a graph, account for the fact that you're talking about ranges of values, as you can see here with how we wrote it, versus here it's just a list of values because all you've been given before is a list.